Good day, everyone. I'd like to start by saying thank you for joining us on this technical topic webinar today. Can everyone please disable their notifications by simply going to my settings, the cog symbol in the bottom right-hand corner of the screen. Go to the notification setting and untick all the boxes as depicted on the screen. Today's webinar, the technical webinar topic is Introduction to Electrical Measurement, presented by Mr. Guy Drew. Common questions asked. Within the following 2 business days, everyone who registered for the webinar will get an email with a copy of the PDF slides and a link to the video recording. Please keep an eye on your junk email folder. For live participants of technical topic webinar, we give a complimentary digital certificate of participation. At the end of this session, there will be a link and a QR code to a short form survey that you must complete in order to obtain one. Once finished, we will make every effort to mail your certificate to you within 4 business days. If you are new to our webinar, here is some information about EIT. We are one of the world's only engineering-focused institutions. We presently offer a variety of industry-focused courses, mostly in civil, mechanical, electrical, industrial automation, engineering, ranging from courses to a Doctor of Engineering degree. Sorry about that. All of our courses are available online and on campus. For some courses, allowing students to study from anywhere in the globe while still experiencing engineering in Australia. All of our vocational programs and higher education degrees are recognized and authorized by the Australian government. But we also offer a number of courses that are specifically recognized under one of the 3 international accords: Sydney, Dublin, and Washington. And I'll leave Mr. Guy Drew to carry on from here, and he'll run you guys through the presentation.
Right, thank you very much. If any of you can see my picture somewhere on your screen with a green t-shirt on, I'm not sure how different that looks to the picture you're seeing under introduction to the presenter. That's me looking formal. I'm not such a formal person, but let's just have a look. Let me just run through that. I've been involved in the electrical side of the world for a great many decades, and I enjoy teaching a lot as well, sharing electrical knowledge. Okay, I hear somebody who doesn't have a muted microphone. If you can hit that mute microphone button, that'll be good. 2 famous sayings that I run with. I'm saying they're famous because I didn't invent them. The one is, if you can't measure it, you're guessing when you fix it. So if you don't know how much something should be, and you don't think and it's not the right amount, if you don't know where you're going, it's difficult to make it right. And the second thing is, as far as electrical safety goes, one thing about electricity, it can, let's use a harsh word here, can kill you. So you want to be absolutely sure you don't guess too much. All right, on this topic of introduction to electrical measurements, it's a very broad topic, and I had a difficult time trying to decide where to start, what to include, what not to include. And we can't cover absolutely everything to do with measurement, but because it's on the electrical side, we're going to start right back in the beginning. I'm So with that over and done, that's sort of an introduction. I am, oh, we still have the agenda slide. So we've got the introduction, which we've pretty well been going through. Mystery agenda for 2, 3, and 4. That's more or less the slides we're going to run through. And then we'll have a conclusion. You can ask any questions at the end. I believe there's quite a lot of people joining us, so that will be an interesting operation. Let's move on. And I wanted to warn you that quite a lot of the illustrations or drawings you're going to see, they are hand-drawn by my hand with, where's the camera? The electronic pen. So don't be shocked by it. I'll run you through them so they become a little clearer. But I wanted to warn you about that in advance. Also, the digital communication is very quick, but from when I move on a slide, I'm going to allow a few seconds for the next slide to appear so that everybody is on the same page, literally. Right, we're going to tap that one, and a bit of ancient history. Okay, you also get to see my first hand-drawn slide there. Yeah, the idea is if you take pictures off the internet, you're supposed to give credit to whoever put them there in the first place. And while there are a lot of pictures of astronomers, I didn't draw them, I didn't take those pictures, and probably back in the 1600s, nobody else took the pictures either. But I don't want to steal somebody else's work. So let's see if I can make this. I'm hoping that you can see a cursor. It's like an arrow pointer pointing at about the 11 o'clock position, moving around on the screen. The interesting thing is that the speed at which I move it, because quite often the screen's only shared maybe 4 or 5 times a second, it might appear to jump on your screen from position to position. Not your computer. We've got limits to how much bandwidth we have. Okay, so some measurement from ancient history. You get recent history, get ancient history from long, long ago. Now, this thing we're going to call measurement. The actual word, if you look it up, I like looking up words, it goes back hundreds and hundreds of years in its various forms. And to actually do it, people didn't speak the English language as we know it 1,000 years ago, but it doesn't mean they couldn't measure. Now, over on the right-hand side, I've got a picture. It's not twin astronomers. It's one astronomer. He's on the left-hand side. He is a bit of a stick character, and you will see that his right arm has actually got 3 joints. That's just one of those things with my characters. He's holding a telescope, and they were fascinated with the fact that if they looked up at night and they saw the stars, and they watched them long enough, the stars seemed to move. So what they would do, take some sort of telescope, and they probably weren't as advanced as the ones I've drawn here. These are advanced telescopes. They'd walk a certain distance off to the right, which they could measure because they had measurement. They knew how far they'd walked. And they would look up through their telescope, and they'd see, now they get a different angle on the stars. They figured out a way of measuring at what angle their telescope was inclined towards stars. They knew where the ground was. They knew how far they'd moved off, in this case, off to the right. And believe it or not, hundreds, even thousands of years ago, they were doing calculations. Now, the reason I mention calculations is that if you throw a structure together, you build it out of bricks. If you haven't taken measurements, it's going to look very haphazard. But you think about the famous pyramids, not only in Egypt, but in South America and a couple of other places where these things crop up. They use measurement to do this. They said, that's too much, that's too small, move it a bit this way, move it a bit that way, until they got it right. So this thing called measurement, it's been around a long time. On some of my drawings, I do put in labels, like how far are the stars away? They wanted to know, well, is that star just maybe 100 meters up in the air, or is it a little bit more than that? They didn't know these things. Somebody had to discover it. On the right-hand side, I said there are lots of stars that you can see. I've drawn 1, 2, 3, 4, but there's a lot of them. And I even drew labels for the telescope so that you don't have to feel bad saying, what is that thing? All right, we move on one. And no pictures on this one, but words sometimes give you a lot of insight into the meaning of what you're measuring. So if you look at the word measure, you think about the word meter, how often it crops up, kilometer, and down here we have diameter, dia to go across, meter, normally used with circles, peri and meter is a measurement around the outside. Peri goes with outside. If you have a city, you have a peri-urban area. It's around the outside. Then you get various fields of measurement. I've only put down a few of them here, but you see how they all end in the word metri, and metri. Geo, measuring the earth. Trigo, measuring a triangle. That's my other beloved subject, maths. And optometry, opto, to do with seeing things. And when we are measuring something, what we're really doing is asking, how much have we got? We could also say how far, how heavy, but all those are measures of how much we've got of a particular something we can measure. And a word, I Googled this word electrometry, and it came back and it said, no results match your search. So I think possibly we've invented a new word here. The metry, the measurement of electrical things, electrometry. If I live long enough, I could write a book about electrometry. Right, we move on to this next slide. I'm just allowing a few seconds for it to make its way through all the pieces of wire and over the radio networks and appearing on your screen. Right, this one is saying feeling a measurement. Now, I put feeling in inverted commas, not necessarily with your hands. It's something you feel inside you. You can't see me patting my stomach here, but that's what I'm patting. That's where you get a feeling. You can get a good feeling, get a bad feeling. When you are measuring something and we're asking, how much is it of whatever? If we're going to make sense of what somebody tells us, we need to have an idea of what we're expecting to find, or we need to know something about the thing we're measuring. If somebody tells me that a particular isotope, that's a chemical thing about which I know next to nothing, has got 4, hydrogen atoms. And for the chemists out there, the chemical people, please don't shoot me down. That might make no sense at all. But if somebody tells me it's got 4 or it's got 8, I have no idea. I have no idea if that's a good thing or a bad thing. And I took an example here of something that's a bit more common. You take a newborn elephant. Now, if we compare it to people, when a person is born, how big's the baby? Maybe it's 2 kilograms, 3 kilograms, 4 kilograms. That's what we expect for a human baby. So if somebody tells you that a newborn elephant is just weighed in at 60 kilograms, you might think, okay, that sounds pretty big for an elephant or something that's just been born. Now, unknown to me, but I thought I'd check it up anyway. Here's a picture of an elephant for you. There's actually 2 elephants. It's lucky we can count. We can see how many there are. I pause there. I just want this picture of the elephant to arrive so that I can take my cursor and move it around the little elephant. Now, that one's not brand new because it's kind of dry and you can see it looks like it's been around for at least a couple of days. These little baby elephants, when they're born, 90 kilograms is about the weight when they pop out. I don't think they pop out. Apparently the mother lies on her side and it kind of slithers out, but 90 kilograms. So now we know about elephants and it's 90 kilograms. You can, at the next party you go to, you can ask people, how big's a newborn elephant? And you can tell them it's 90 kilograms. It's a measurement. If somebody told you it was 200 kilograms, then you have a feeling something's not right here. It's got to be less than that. And how do we pick up these feelings? It's experience. When you work through a manual on a piece of equipment, they'll give you specifications throughout. Those specifications need to have a meaning, not just a bunch of figures that you say, okay, I got that measurement, I'm within tolerance, let's move on. You need to have a feel of what you're reading is right or wrong, even without looking at the specifications. But now this is an electrical talk, so let's find something electrical. And we have some people. We need to know where things come from. We talk about volts and ohms and amps and watts, and we need to say, well, where did the words come from? So from now on, the volts, we have here Italian gentleman, Alessandro Volta, 1700s to the 1800s. That's when he lived. A French gentleman, I'm pretty sure he's French or maybe Swiss, but his surname, Ampere. I couldn't get the E with a little dash on it on this particular text I was using. Ohm, you've heard of ohms lots of times. Did you know it was named after George? I don't know how to say that name without an E. His middle name was Simon or Simon. I think he was German. And we have James Watt, who was a man from Scotland. A lot of things together and came up with power, not only in electricity, but he then came up with steam engines, and these were busy people back then. And I put the dates of birth in here, not because you're going to get a test on it or have to remember when were they born, like a regular test question, just to give you an idea of how long electricity has been around for. So you add 300 years onto most of these, so not even 300 years, and we've gone from discovering electricity and formalizing it and making battery cells to having this lecture where I talk here in South Africa and you are picking it up in Africa, Asia, Australia. Right now it's, to give you an idea, it's 18 minutes past 10 in South Africa. But let's have a look at these people. I took these pictures of encyclopedia. In the old days, we used to have books called the Encyclopedia Britannica. You could browse through them, pick up information. But if you want to learn more about these people, that's the place to go. I said here photographs, the art of photography, where you could actually have light focused on a particular flat surface and make it remembered. Odd way of saying take a picture. But before, you could project a light like you can with a magnifying glass, but you take it away and the picture's gone. But they found a way of fixing it onto a piece of paper, late 1820s. And sad to say, if I look at most of these people, these were before the age of photography. But somebody obviously made some sketches. Okay, we're going to talk about electrical measurements now. And on we go here. Now, in a couple of seconds, you're going to see a multimeter turn up on your screen. It's probably, I said it's probably the most mass-produced multimeter on the planet. This particular version of a multimeter is cheap. The earlier versions weren't too bad. The modern versions, they want to save money. And as we'll see now, we're just going to walk around this thing, and you'll see that there are things to look out for. When I'm talking about a measuring instrument, I'm quite sure that a lot of you operate from workshops where you have very expensive equipment on the shelves. You tend to call those things instruments, and it's a measuring, I'm not going to call it a thing, it's an instrument. It can do a job. And I said you can measure Alessandro's, Andre Marie's, and George's on this thing. But nowadays, we just call them volts and amps and ohms. We are going to walk around this. Oh, let me give you a piece of live information about life in South Africa at the moment. We're kind of running out of electricity because the power stations haven't been maintained for a while, like about 20 years. So out of our whole, I think just under 50 gigawatt of installed possible power, we're running now at about 22 of those gigawatts of available power. So we have this thing called load shedding. It means they switch off large parts of the country all day long, not all day long, but rotating. We're off for about 10 to 12 hours a day, and the power went off about 10 minutes ago. But we have batteries, electrical things. All right, let's go have a look at this meter here so we can get into some measurement here. Let's walk around this thing. It's lying down because I wanted to get the whole picture of this multimeter in without squashing it top to bottom. By the way, multi means many, meter is to do with measure, and I put R in the back bracket, so a multimeter. You could also call it a multi-measurer, although people might think you're a bit strange. You'll see at the bottom, now just bear in mind this meter is lying down sideways. So when we're talking about the top left of the meter, the top left, where the cursor's wandered across to under the EIT symbol, we're taking that as being the top left. Come down a bit to where the dial is, and we see first one we got here is DC volts, short for direct current, voltage. Voltage measured in a circuit where the current's pretty well all flowing in the same direction. And we've got a number of ranges we can switch it on to. They don't specifically mark 200 millivolts, unless that's what was underneath that scratch. If you poke this thing with a soldering iron, little bits of plastic disappear. 2000 millivolts, same as 2 volts, 20, 200, and 1000. We'll come to that. We've got an off button. Why does it have an off button? Because this one is a powered meter. It's got a battery in it. I'll show you one later on that isn't. We can measure AC voltage in a circuit where the current is varying and the voltage might be going up and down, maybe positive, maybe negative. On these meters, we're a bit stuck for space, so we don't have 5 voltage ranges. These numbers here are supposed to tell you what the maximum value is that you can measure. When we get nearer the probes, we'll talk about that. Next one round, direct current amperage. On the budget meters, you tend not to get AC amperage. When I say budget, I mean like small, and not just small in price, but small in value. They cut out as much electronics as they can, because every few cents they cut out, it means they either charge less or there's more profit in it. We have also direct current. It's got its own socket here, 10 amps for high current measurements. We'll talk about that as well. We've got transistor gain measurement, not used so much anymore, but nobody's about to change the design. We can check diodes up to a point. We'll mention that. And we have resistance measurement. So there's a lot of measurements you can make on this. And for most domestic, sort of at-home measurements, it pretty well does the job. There's writing down the bottom here. So on the next slide, we're going to go and have a closer look at that. While we're still on this one, if you look at the actual display here, you'd think, what are these funny symbols here? It looks like an L and some other symbol. Those segments have died on this meter. I have a good feel for what they are. So if I see that segment missing and the other 6 are in place, I'm pretty sure that's either a 0 if we put that one in, or it's an 8 if we replace that one and that one. But I know the middle one, segment G, isn't missing. It's working, so I know it's a 0. But this is my own meter. If you bought one from the shop like this, you'd want to take it back and say it's missing something. Right, let's go and have a look at the writing on this meter, close up. Give it a few seconds so that it arrives where you are. This, I'm moving the point of the cursor around the CE marking. Off to the left of the screen, you should see a large C and a large E, and it's drawn on a grid showing you just how precise this particular marking is. The marking, it's a European Community mark, and it's supposed to relate to a whole set of standards for safety, not only in electrical meters, it can be to do with noise or pollution, but in our case, it's supposed to relate to the safety of the meter. Now it's up to the manufacturer to plant this thing on their meter. Sometimes you'll see that this part of the E stretches out and is level with these 2 edges of the E. Then you know we're not talking about a CE mark. Sometimes the E will be a whole lot closer to the C. If somebody puts that on, and I mean somebody can really put any marking on at all, there was a rumor that was put on to indicate a Chinese export. The powers that be say that's an urban myth or just a made-up story. if this is relating to electrical safety, it's supposed to be telling you, specifically on a meter, there should be a voltage rating next to it. It tells you which set of directives or safety standards this meter is working to. So this one sitting here by itself, it's got the right sort of shape. The manufacturer puts it on. If this product arrives in Europe and somebody checks up and says, you don't have a license to put this on, then there could be trouble. The cat, oh, well, okay, let's go have a look at this cat 2 thing down the bottom. And then we'll look at these other markings on it as well. The cat, C-A-T, it's not cats and dogs, it's short for the word category. You get cat 1, 2, 3, and 4, and it basically relates to the level of voltage that you can use this instrument in. Different zones in the electrical environment get referred to cat 1, 2, 3, or 4. Cat 1 is the lowest one. Maybe in a household where your highest voltage is 200 volts. The idea is it's not quite as dangerous, but electricity is dangerous. This one claims to be a cat 2. They claim to have manufactured it under a CE directive, so perhaps they checked it. This meter is pretty old, so it was made when things were made a little more properly. Now, look over where the probes are. These probes are pretty close together. They're not both the original probes. You can see they've got a different shape. The marking here tells you 750 volts AC. It's got a red zigzag line, which is normally short for lightning. It says warning. I would not plug this meter into a circuit 750 volts. I have connection onto a 3-phase circuit, 380, 410, and I get nervous if I was going to do that. But that's only once or twice. I have a different meter for doing that. 1,000 volts DC between this point and this point, I think not. Not putting 1,000 volts there. See all the sort of dirt residue that's on top of the meter? That is bad news for any sort of arcing. Now, these are recessed sockets. So the actual probe has got a plastic shroud around it, and that gives you an extra measure of protection. But would I connect 1,000 volts onto this meter? Nope, not happening. International warning sign, 500 volts max, and a ground or earthing symbol. It means you don't want to connect either of these probes to a point in a circuit that's sitting more than 500 volts above earthing level, because quite often your feet are where the earth is. Right. So we got warning signs, not too bad. We're going to have a look inside this meter. I just want you to know why I'm not going to connect 1,000 volts on here. And then Ohm's Law, George, Simon, Ohm. Let's see. Oh, it looks like the same meter, but it's a different one. When this one's arrived on your screen, I should count down, 3, 2, 1, 0. You'll see the CE mark has disappeared, and there's no Cat 2 marking on this one. So this manufacturer isn't making any guarantees about safety concerns as far as how they've manufactured it. This model is slightly different. Over here, it's got a sort of square wave. Well, it's not really a square wave, is it? But it's got a pulse waveform. I guess that comes out of one of the sockets. I'm not sure which one. I've never used that function. I have a lot of these meters. Some have blown up, some not. They've got an interesting warning here for the 10 amp reading. For the 10 amp reading, you don't, this red plug that was in here, you need to pop it up into the 10 amp reading socket. They tell you it's unfused. It means that if you connect it to a circuit and maybe there's 100 amps flowing, there's no fuse that's going to blow and protect your meter. If you have a fluke multimeter or quite a few of the more upmarket ones, yeah, they have fuses in there, special fluke fuses, safety fuses. This one, it says it's unfused. It says you can measure 10 amps maximum for 10 seconds. It means after that, you disconnect it. It's partly because of the meter, and it's partly because of the leads that get supplied with these meters. Those leads are not designed to carry 10 amps for any longer than is the bare minimum time necessary. And it does say once you've made that measurement, you can do it 15 minutes later. So they're giving you a warning, even though they have no CE rating or CAT rating. They have the same voltage arrangements here. It's telling you what the maximum is. It's a warning sign. You see on this one, they left off the 500 volts. So somebody might think, well, hey, do I need to connect this common point to ground? It's amazing what small markings can lead people to think. You need to read markings on a meter, and you need to feel in your stomach, is this okay? You don't feel with your finger. You can find a lot of workshops where somebody will boast that they can measure 220 volts or 110 volts, depending on where you are in the world, with their finger by the amount of buzz they get. Not recommended. Okay, I promise you we're going to get some Ohm's law. Let's go have a look. Oh no. Oh, well, there's a bit of Ohm's law. Okay, this is the inside of that meter. So we had the negative socket down the bottom, positive one in the middle, and this one up at the top is the 10 amp socket. So what would happen when you're measuring a 10 amp current? You want to put in as least resistance. You have to break the circuit open and insert your ammeter. When you were back at school, they used to tell you voltmeters, high impedance or high resistance, and ammeters, low resistance. So between the common, the bottom one, you have this copper shunt, and it's connected up to the 10 amp socket on a printed circuit board track there. And here's a bit of ohmage here, R0.01. They're telling you that this piece of copper wire, it's a piece of copper wire. Some people will say, no, it has no resistance, it's a piece of copper wire. Everything has resistance, even if it's very small. But there's no fuse between that socket and that socket. But now have a look here. It means that effectively the negative terminal of this meter is connected to this socket, which is maybe 10 millimeters away from the positive socket. And at some point, this particular meter has maybe got damp, had some water in it. You see this corrosion on this board. The bare board by itself can maybe withstand 1,000 volts between these two terminals. With corrosion on, that's why I don't put 1,000 volts on a meter like this. You don't know what's happening inside. On the expensive meters, they coat the whole printed circuit board with an insulating shellac layer, which reduces, let's just say reduces the chance of any corrosive buildup touching the metalwork. That's why I don't put 1,000 volts on here. I did say Ohm's law, didn't I? Okay, if you pass 10 amps through a 0.01 ohm resistor, you multiply the two together, V equals I times R, you get 100 millivolts. So effectively, when you're measuring 10 amps, the rest of the meter is set up as a 100 millivolt meter. Now, I did want to include some other slides, which I see I left out. So while we have this one here, that little item there, surface mount resistor. Yeah, I'm so scared of those when you're talking high voltages anywhere in these meters. The older meters used to have large resistors, and they'd be fireproof as well. Here we can save a bit of money. I'm not saying this particular resistor would be under stress, but I don't like little resistors where you're talking voltage measurements. They scare me. That's just me. Maybe I'm a coward. I like voltage points that are going to have lots of voltage on them to feel separate. You look at it and say, no, that's a bit too close. If you've ever looked at all those tracks on a computer motherboard running maybe 0.1 or less, 0.05 of a millimeter apart, you don't want to go putting 1,000 volts between those tracks because your feeling says that's not good. You've got to trust your feeling. Right, let's move on. And we see, okay, analog meter. So the other one was a digital meter. It gives you a reading in digits. This one has digits on it, but they're kind of printed on. 20, 40, 60, 80. It's an analog meter. It doesn't go up in steps. This needle can move anywhere on the dial. I'm quite a fan of these. And this meter I bought from a shop. When I was younger, I made a multimeter, and I couldn't understand any of the calculations. It took me forever. But it tells you that this meter, measuring microamperes, microamps for short, if you put 100 microamps through here, you're going to get a full-scale deflection, which means this needle is going to move all the way across to the 100 when you somehow cause 100 microamps to flow through the meter. Now, what is inside this meter? I said there's a coil of wire. It has resistance, a bit of ohms there. It's got some magnets. It's got a bearing, 2 bearings, and it's got a pointer. And we need to know what makes this pointer move. Now, one of my famous, well, they're going to be famous soon, hand drawings is coming up here. North and south meter, magnet. We have a coil, and this coil is pivoted in the middle. It's got a couple of bearings, so it can swing. It can rotate clockwise and anti-clockwise. Some meters, this coil will be, what should we say, in parallel or in the same direction as the needle. It depends where the magnets are. But the idea is to show that when you pass current through a coil, it generates its own magnetic fields with north and south, and they either push away from these two or they pull towards them, and that causes the needle to move. Now, the one slight disadvantage of this sort of thing with a mechanical movement is that if you drop it, there's a good chance that you're going to damage it. It's very finely set up. If you squash the bearings, you don't get a proper meter reading. This one is sitting on naught. This one on the right is a center zero meter. So it can measure a negative current off to the left or a positive current off to the right. And I say, if you look inside a meter, you will see the coil sometimes sitting at that angle. But it's the idea here. I thought I'd show you the same pair of meters. We're putting 50 microamps through them, and the one on the left is moved up to a 0 point. Again, other meters would have the coil at that angle. The more I look at the slide with the north and the south, I kind of wish I'd drawn the coil in vertically rather than horizontally, but it's the idea we're looking at. So we have 50 microamps flowing through that meter coil. On this one, I need to go and look at that purple sign down the bottom. I see I'm not sure if people are putting their hands up or not. I'm not too sure. But in this one, we're putting the current backwards through the meter. On a digital meter, what do you see? You see a number with a minus sign in front. Here, when you reverse the current, the needle tries to go backwards. And if it's quite a serious overload, it hits itself against the end stop. And it can bend, or it can even get stuck. Not so good at showing negative voltages or negative currents. Whereas our center zero meter, it can go left, right, positive or negative if we reverse the polarity. Oh, yes, this is reversing the polarity from the previous picture. There's another sketch coming up. Now, here's a reading for a full-scale meter. The reason I'm just looking at all these analog meter measurements, I had to decide where to start, and I thought having a feel for when you see a needle move, what causing it to move, and how much it's going to move by, and getting a feeling of when you're going to overload this thing. We said earlier, full-scale deflection, FSD, that's when the meter is as far as it'll go. The resistance of the coil, it varies from meter to meter, depends how sensitive it is. Ammeters will be a few ohms, if that, and meters intended to be used in voltmeters can be into the thousands of ohms, very fine wire. And we'll normally have a resistor in series so that we can actually put a voltage across the two terminals, and the voltage will cause a current to flow. We don't want all the voltage across the coil, so we use a dropping resistor. And we're about to come to Ohm's Law. It is coming. It is coming. And it's going to come to an an actual marking you are going to see on a meter. I've connected a voltage source here. I call VN, voltage N. Current is going to flow through this resistor. We're going to drop some voltage across there. The current times the resistance value. There's going to be a certain resistor value that will cause, in this case, 100 microamps to flow, full scale deflection, when you've got 1 volt. Now, Ohm's law says we can work out what that value of the resistor is going to be. So, I think I said that on the previous slide. Yeah, to get, oh, you know what, I just moved the whole thing across, the whole picture across. Same picture, we want to know, on a 100 microamp meter, if we want to apply 1 volt, exactly 1 volt to those terminals, what resistor do we need to put in here? And Ohm's law relates the resistance, the voltage, the current, the meter resistance, and the source resistance. We take that as one big lump of resistance. And to get 100 microamps flowing through the RS and the RM, if we're putting 1 volt on, we divide 1 volt by 100 microamps, and we end up with 10,000 ohms, or 10 kilo ohms. And this is going to give us a specification for this meter movement of 10 kilo ohms per volt. If we wanted to measure 2 volts and get full scale, no, let's go for 10 volts, because it's got 100 at the full scale end of the meter. We would need 10 times the resistance. So we start off by knowing what the resistance per 1 volt is, and we can work it from there. We don't need to know how much RM actually is, as long as we know that this meter has now got something called a 10 kilo ohm resistance per volt. Now, I had a quick look at the time here, so I'm going to move on from some of my pictures here. Briefly, we'll mention, if it's a more sensitive meter, 50 microamps full scale movement, we have more resistance. 20k per volt is pretty standard, used to be. If you see this on a meter, just want you to know what it actually means. Really expensive meter, hypersensitive, we could get up to 100 kilo ohms per volt. Why is this important? When we're measuring voltage, we don't want to put heavy loads on a circuit. So we try and get this value as high as possible. You could even take an ammeter, a real ammeter, and turn it into a voltmeter by putting some resistance in series, but not a good idea. That's my sad emoji. I don't know where to find one of those, so I drew one. Or it's like a cross emoji as well. It's supposed to be more sad than anything else. I'm just going to click on this collaboration panel. 50, okay, I don't think I need to do anything with that. I'm going to close that one off. The reason I've put in this idea of using an amp meter and turning it into a voltmeter, you don't want to do it. Simple circuit down here, you've got a 12 volt battery and you have 2 6 ohm resistors. You know, there's going to be a 6 volts across each one. You could use Ohm's law. You could say there's 12 volts, 12 ohms altogether, current of 1 amp, 6 and 6. We know theoretically there is. But now, what happens if we go and use the wrong sort of meter? Well, out of the ones we looked at, we said the 1 meter would need up to 10,000 ohms altogether to measure 1 volt. So if we wanted to turn it into, say, a 20 volt full scale meter, we're going to go up to 200 kilo ohms, what we'd call the input impedance of the meter. If it was a more sensitive meter, we might go up to 400 kilo ohms. Not so much the figures that are important here as the size of them. They're big. You want to measure voltage, you want big numbers here. Our small ammeter, we'd end up with only 20 ohms, so that when we put 1 volt across it, it would read full scale. That's not good for a voltmeter. That's not what we do with voltmeters. Our bigger meters, you measure with 100 microammeter range, 200 kilo ohms in parallel with 6 ohms makes no difference. We're going to read 6 volts. The moment we put together our badly made up, where we used an ammeter meter movement, and we've only got 20 ohms, that is now comparable with the 6 ohms. It's going to affect the reading. If you want to do the calculations, you'll see that it actually drops this. What was 6 volts, the meter influences it and brings it down to 5.5. That formula there is derived from that 1 over R plus 1 over R, the original parallel ohm formula. Okay, here's a real one. Also a budget meter. A couple of things here. You'll see down the bottom right corner, 2 kilo ohms per volt. I sort of hacked away at this figure up till now, just so that you have, when you see that, you'll know what does that mean. It means for on a given voltage range, there are 2 kilo ohms of resistance between the two terminals for every volt that you're measuring. If you're measuring 250 volts, there's going to be 500 kilo ohms of resistance. Not too bad. This thing you can see over here is a mirror. It's not bad for a budget meter. You know why you have a mirror here? I don't know if you can see over there, there's a red reflection. The idea when you measure with one of these sort of meters is you mustn't see that reflection there. The needle must be sitting right on top of that reflection. Then you know your eye is exactly above the correct measurement. At the moment, we are off to the right-hand side, so it's not going to read correctly. But if you ever wonder why there's a mirror, it's not for checking if you're getting something out of your eye. It's because we're trying to get an accurate measurement. Okay, I thought we'd just throw a bit of electronics in here. For you, any of you in the electronics world, you get an integrated circuit called a 555, very famous, been around 40 years. It's called a timer, but it's really an oscillating circuit. It makes an output go up and down and up and down. And it does that by having, from a red positive voltage supply, current comes through these 2 blue resistors, big one, mega ohm, charges up a capacitor. The IC senses when it's reached a certain voltage, which is about 2/3 of whatever you've got up here. And it does some clever electronic stuff inside, and it brings this point here down to ground, and it discharges the capacitor. When the voltage on the capacitor drops down to 1/3, it'll start going up, and it goes up and down and up and down. If you take that other meter we just looked at with its 20 kilo ohms of resistance, and you touch it on this point across the capacitor, the circuit will stop working. Because now this voltage here, we could work out voltage drops here. It never actually reaches 2/3 of the supply voltage anymore. So the measuring instrument has interfered with the operation of the circuit. That's bad news. If you go to the doctor and he puts a stethoscope on your chest, when he puts it on, you don't want that to interfere with your heart beating. It's just supposed to measure it. The instrument mustn't interfere with whatever you're measuring. Important thing. When something isn't working, you've got to have a feeling. What did I do that could possibly stop working? You've got to have an idea of what's inside a meter that could possibly influence what it's doing. Now, this is the bottom half of that other meter. Slightly dangerous thing here. You have 2 terminals, and they're used for high voltage, 500 volts, and for measuring current. Can be a dangerous thing. I've drawn a yellow arrow here because I didn't turn the selector dial around, and I should have done. So imagine this is where the meter is. We're measuring current. So now, in your mind's eye, you know how much resistance there is here. 1 ohm. We want small values so we can measure current going through. And that's fine. We're going to measure up to, I think, 250 milliamps. Now, let's say you now move your meter to a different circuit where you want to go from measuring a small current to a high voltage. I'm allowing a few seconds here. What have we got here? 220 volts coming in, AC. That's a sideways AC sign. bridge rectifier, smoothing capacitor, means we're going to get about 300 plus volts across here. And you want to say, am I getting the voltage here? But you forgot to change the range over. So what's happening? You are effectively connecting a 1 ohm resistor, because you didn't change the range switch, across 300 volts. Now, Ohm's law, even without Ohm's law, 300 volts over 1 ohm is 300 amps. That's a lot of current. It can do damage. And this is the danger of having the same pair of sockets for measuring voltage and current. And you know what's going to happen? That's going to happen. Now, I did say it's the same meter because I think I'm going to take one of my meters and actually put 300 volts on the current range so that I can take a picture of that. But everything will melt and it'll probably explode in your face, or the leads will melt in front of you. So we want to be very careful. We've got to have a feel. Okay, I'm measuring voltage, measuring current. I know what it looks like inside the meter. There's a limit how much protection it can have. You've got to feel these things. You know, sometimes you want to measure a current in a high voltage circuit. 220 volts AC over there, a squirrel cage motor running on 220 volts. And these are our leads. They haven't fried yet. They just look a bit wobbly. I wanted to show they were our leads. And let's imagine that you had left the meter still switched to current, because we want to measure current. And it's got an overload fuse, so if you put through more than 250 milliamps, it should pop. But what you don't know is it already popped, and somebody else in the workshop went and put in a 10 amp fuse in there just so that it didn't pop again. So now you go and connect this, and what happens? Too much current flows through here. It doesn't pop the fuse, and this shunt current resistor melts or pops. So let's take it out of the circuit. There, it's gone. Now you end up with 220 volts across the insides of your digital meter, and it'll go pop. It might buzz, it might smoke, it might catch fire. We have to know what's inside these machines. Nobody told you they changed the fuse, so the manufacturer did tries. In some cases, they do have a protection fuse, but that's the end of the meter. I have several meters that I've destroyed. It's my fault. Okay, just a few quick ones here. This is where you're feeling things. That's a car, the red bit. That's a pair of jumper cables. They're not connected to anything, don't worry. And here is a piece of ripcord or alarm wire. It's 0.2 millimeters. You've got to say, would I know which pair of wires to use for jumper cables? You'd think, obviously, you're going to use the thick ones. I have seen people using thin ones. They don't have a feel that says, ooh, thin wires. How much current for jumper cable? Maybe 10, 20, 30 amps. This is too thin. And they hang this wire over the metal part of the car. What happens? The wire gets hot, it melts, touches the car, and you destroy a lot of batteries, and then people cry, maybe it catches fire. We need to feel these things, thick wires for the right application. And what do we have over here? I see we're up to 10:55. Sure, we still need to have time for Q&A here. So this is the last slide we're going to look at. This solar installation, I know they're all around the world, but we particularly need them because of our power outage problem. You want to measure high current. This is a clamp-on meter. It's got jaws, and what's slightly different about this one, you can measure DC current as well. So it's not just the magnetic field, it senses the electric field from a DC current passing through here. It's got Hall effect sensors, but the bottom line is a much safer device to use. So we don't go connecting high currents to the inside of this thing. It even has an NCV, non-contact voltage. So on the end of this, it'll pick up an electric field if you bring it closer to a wire carrying a live voltage. I was going to go into some solar measurements, but we are due to be here for an hour, and that looks like in another 4 minutes. So I'm hoping that my good colleague here, Mr. Malefi, are you there? Because that was the last slide. I think if I click this on one further.
Yes, I'm here. I'm here.
Okay, look, I've talked about a lot of technical things. I know what we do now as far as Q&A goes. I sort of ran very close to the limit here.
Mm-hmm. Thank you very much for that, Mr. Dree. That was a lovely presentation and very informative. And I'm guessing that everybody enjoyed it that attended. We have a range of upcoming programs in electrical engineering. To see our full course schedule, please kindly go to the link in the chat box, which I will provide you now, guys. And with that link, you can see a range of our courses. And for those who are still, sorry about that. If you're still interested in the upcoming webinars, as you can see on the screen, those are our next upcoming webinars. And I'll provide you guys with the link also in the chat box to see more upcoming webinars. So with the link provided, you can go to it and you'll see a couple of our upcoming webinars. To receive your digital certificate of attendance for participating in this webinar, please fill out the form and survey here or scan the QR code. I'll provide the link also for everybody in the chat box to do this. And yes, on-campus facilities are available. They're in Australia. We don't have yet in South Africa and other countries yet, but yeah. So I'll put the link again to the survey so that you can get your certificate of attendance. I'll leave it for 2 more minutes for people to scan, for those that are scanning and for those that are taking the QR code to do that. And thank you. And now is the Q&A. For those that have questions, please do ask now, and Mr. Guy will answer any question that you guys have that's related to the topic presented today.
No. Sure. Just getting used to this. Am I going to see any hands going up?
Yes, you go to you see the chat box. Go to the chat box and you'll see all the questions asked there.
Okay, let me find a chat box here. Where am I going to find this chat box? Are we looking top left or bottom right?
Bottom right, the first icon.
Open data visualization panel. Is that in the? I'm wondering if I've got the right set of icons here to see any hands up. Can you see any hands up?
There's questions. No, there's no questions at the moment. I don't see any questions. Okay, we'll give it a little bit of time and yeah.
Yeah, I'm just sort of making my way around the screen and I was just trying to open that chat box.
Can you see it at the bottom right hand corner? There is
Yeah, I got.
4 icons. Did you see it?
I have got 3. From the right, I've got the purple one that opens the settings. I've got one that says Open Data Visualization Panel, and I've got one
Press the purple one.
purple one. Okay, purple one open.
Wait,
Oh, yeah.
do you see the chat?
Now I've got my my settings, share content, attendees, and chat.
Yes, then you go to
Okay,
chat.
I see chat. Okay, so
Then
we've got.
Collins asked a question.
I've got Charles from Zimbabwe. Okay, let's see if we're going to
Yes,
click
you
on one of
can
these.
follow us on Instagram and YouTube. I'll provide us with the links. And yeah.
Oh, okay, this was Charles back at 10 to 10. He said he couldn't hear me. Charles, I hope that got better.
Yes.
And Rashad,
Jerome asked the question. He's like, what uncontrollable variables can be considered when creating a circuit?
okay, uncontrolled variables. Yeah, if you create a circuit and you take it directly from a drawing, and where there's an electrical connection on a drawing, you put a piece of wire in. Uncontrolled variables will be where you think you don't know you're going to measure 10 amps and you use it like a really small piece of networking wire and the thing burns up in front of you. I guess that would be an uncontrolled variable. It's where signals come in that you hadn't expected, where you pick up noise and you get mistaken readings because you're not picking up readings from a particular circuit, you're picking them up from outside noise. If you run cables over a switch mode power supply like a laptop charger, you pick up all sorts of nonsense. If you run your network cable over that, you could suddenly find, I don't have a connection anymore. So, yep, there's quite a lot of those.
Then Collins asked the question, any emphasis on the, yeah, I can't pronounce this word, guys. I'm sorry.
Are you at the top or the bottom?
At the bottom. By
okay,
Collins.
my bottom. Okay, I've got Terrell. I've got. Where's Collins? Yeah, I should. I'm trying to find Collins. I want to scroll this chat box up. I'm only getting the most recent ones here. Oh, there's Collins. There we go. Any emphasis on the potentiometer adjustment capability on the digital multimeter. Look, the average digital multimeter tends not to have any outside adjustments. It depends if you're talking about ones you'd find inside for calibration. Collins, on your question there, you just have to tell me what sort of potentiometer adjustments. On an analog meter, you get an adjustment for setting the zero of the ohms. So we would have to have a look at that one, Collins. You might have to redo that question, slightly worded differently.
Then there's Andreas.
Yeah, I've got. Okay, I see Collins talking about the adjustment inside. Reset a QR code. Collins going to come to that. Brian, George, thank you very much. Yeah, I hope you got something out of that. The span is too small. What does it mean if the span is too small? If you were looking at an analog meter and you're trying to get a lot of small voltage measurement, So let's say you're trying to measure the difference between 10.01 and 10.02. If the whole span is, say, 20 volts, you might struggle to get that sort of difference on an analog meter. Digital meter, you can start reading the digits. Just going back to Colin's question there, internal measurements for proper measurements, internal adjustments. You've got to have something accurate to be able to set the calibration up so your meter reads 0 when it's 0 and full scale when it's full scale. If you haven't got an accurate measurement, you're still doing a bit of guesswork. I say it's mostly the older, or let's say the analog meters, which you can still get, that have that sort of adjustment. Emmett, you said, please elaborate it. I did. Oh, yeah. Now, this is where I would need for Emmett's question, please elaborate on the span. I'm going to see if I can find that whiteboard. I did find it earlier. On Andreas, why was a series of resisting current for voltmeter a bad idea? It was a bad idea when we were trying to use an ammeter turn it into a voltmeter. An ammeter by itself, the coil resistance is low. It might not even be as much as an ohm. So you've got to put a series resistor in series with it to make it think it's a voltmeter, but you're only going to have a couple of ohms in there. And when you're measuring voltage, you want to draw as little current out of the circuit as possible. If you draw too much out, you load it, you change the measurement, and you could even get a surprise when your meter starts overheating. So it was a bad idea for using a resistor with the ammeter. If you're using a micro ammeter, milliammeter, no problem. That's how we would do those things. John Constable, rare earth element, whoops, that one jumped. Made things smaller. Okay, John Constable. John, that question there on the, let's say, the physical side of magnetism, there's something about them the same way they discovered that graphene is a whole lot more efficient than various other elements for solar power, amongst other things. Not my expert area. That one, I can't give you a really good answer on that one. How often should a meter be calibrated from Demendra? If you're in a factory that's governed, or a workshop that's governed by specifications, they normally have a set period. It depends what you're measuring, what sort of instruments. It can be as often as sometimes once a year, once a week. It depends how critical that measurement is. If you're a calibration lab, I would guess maybe it's a regular daily operation. You also got to know the drift factor of the piece of equipment as to how much it's going to drift. The average multimeter, though, even the cheap ones you buy in the shop, they will hold their readings for like even years and years and years. So it really depends how critical it is to get down to the last 0.001%. Samuel Garner, what brings the pointer in the analog meter back to rest? It's got a circular spring. So when you put a current through the coil and the magnets, the coil magnetism pushes away from the permanent magnets. If the spring broke, that needle is going to sit against the other side of the meter and it's going to stay there forever and ever. There is a coil spring. And if you've got a center zero meter, it's got two springs and they're wound in opposite directions so that it effectively brings the meter back in the middle. On the analog ones, you'll also see a screw adjustment on the meter face where you can actually mechanically set the 0 point. Aaron, thanks. Your pleasure. I hope you got something good. John, okay, John's good. How can a normal measuring instrument be calibrated? Kelvin, you need to have something that you know to be 100% accurate. You can actually buy standardized, like if you want to set up voltage, you can buy integrated circuits that are guaranteed to have been trimmed down to something like 0.01%. Analog devices have some of those. You can at least calibrate voltages from that. Okay, Samuel, circular springs, circular, oh yeah, look, I guess all springs can be circular. It's more like what you call a hairspring. It's wound from the middle and it goes out in circles. If you can still see the pointer, I'm going to sort of do almost like a spider web, that sort of spring. They used to have them in the old watches where when you wound up a watch, you made the spring tighter and then it would unwind. I know somewhere there's a board for sharing a board, and then I would have drawn them. That would be the circular springs. They're flat and they're wound in a spiral. Digital accurate meters, more accurate or reliable? Look, accuracy, we've just got to know they can give you 8 digits of readout and they can still be totally inaccurate. You just get a very high resolution, inaccurate reading. Reliable, if I had to drop a meter, I'd rather drop a digital meter in a rubber casing than an analog meter. Those movements are very sensitive and delicate. When you're wanting currents of a couple of microamps to cause mechanical movement, you've got to know those things are set up that you put a bit too much force on them, I'm afraid they're going to, it's like, what can I say? Reliable, there's a make of analog meter called an avometer, and the AVO is short for amps, volts, and ohms. They were built like tanks, and you could drop those things and they would come back and smile and ask for more. Modern ones, they're reliable if you treat them well. They're not good in strong magnetic fields because the whole operation works on a magnetic basis. So they've both got pros and cons on that. John, like a clock spring? Yeah, exactly like a clock spring that you can wind up, and all the spirals are sort of wide open when it's unwound, and as it tightens up, what you're actually doing is bending a piece of metal. And if you take a flat piece of bar and you bend it, it'll go back to where it was if you don't exceed the limits. A spiral, a clock spring, is like a long piece of very thin, flat metal bar. And when you tighten it up, it's actually bending it slightly. We got Demendra, which category meter is good? Look, Cat 4s are more expensive. I'm guessing you're talking about that sort of category. You can measure any voltage. They are ultra safe. Well, very safe. But if you're only working on DC voltage, you can get by with a Cat 1 meter quite happily. That will measure up to 200 volts and you'll be reasonably safe. The meter won't explode in your face.
Okay, Mr. Guy, we'll have to take one more questions and wrap it up.
Okay, I'm going to go Charles G at the bottom.
Yeah.
Difference between earth and neutral. Look, the idea of earth and neutral. Earth neutral live. If you took a battery and you take the negative terminal with a big fat piece of wire and you stick a big earth stake into the ground, wet ground so that it conducts, the negative terminal is effectively neutral, and the earth, the big lump of earth underneath us, that's the earth. The idea is that's all at a zero potential. If we're standing on that, we don't get a shock. The live is in, say, the plus 12 volts terminal. Earth and neutral, back at the substation, they're actually joined together. It's only when it comes into your house they sort of separate. They should be close in potential. The idea is you shouldn't get shocked from either of them, but people swap them around, so you trust nothing. You always measure to make sure. Okay, my colleague says we're going to stop at that question, so thank you everyone for staying in around. Thank you for all the questions. Maybe we'll meet again soon.
Definitely. Sorry to be the party pooper, but yeah, that's the end of our time today. And thank you guys for attending this. It was really nice to have everybody in. And again, thank you very much. And our contact details are on the screen. I'll leave these for 2 minutes for everybody to get them. And yes, thank you again. And thank you, Mr. Guy. The presentation it was lovely indeed. So thank you very much for that.
Well, thank you for inviting me here. Okay, we're saying hello and thank you and thank you and thank you and thanks. Well, Thank you to everyone else. I'll stop talking now.